on the presentation. And so we're going to be talking about precisely what happens with these chemicals once they are applied to whatever land use we are talking about, agricultural by and large, but also in urban settings, transportation lanes, and others. And what happens to these chemicals once there is rainfall and potentially runoff, and then they get transported. And without any control, they could enter very rapidly. Remember that these rainfall runoff events are fairly short in time. And what happens is that without any impediment, they will eventually make it very quickly to the surface waters, waterways, water bodies in general. And that will immediately cause a pollution event. So the idea is how to control these substances from moving from the land into the water. And this is what the subject of the presentation is going to be about, which is using this vegetation. And here you have a few examples. So the idea is that let me get my mouse in here just for a second. I think I can do, oh, maybe not. I knew how to do this, but not now. Anyways, can you see my mouse, I guess? Okay, so in here on the right-hand side of on the left-hand side of my slide, you can see the land use. And again, it could be urban, it could be agriculture, whatever. And then from there are chemicals, but very importantly, the first two phases we're going to be tracing in these chemical pollution events are going to be the liquid phase, the water itself, the runoff, and also the solid phase, which are going to be sediments. Because chemicals are attached either to the sediment or dissolved into the water. So there are these two phases, liquid or dissolved and sediment bonded or particulate. Those two are usually the ones that answer for the transport of chemicals. And how a chemical attaches or not, or is mostly in dissolved or attached, depends on the chemical characteristics of the product, okay? So before we go there, let me then show you that typically what people have been doing for many years, and somewhat empirically at the beginning, was just putting this vegetation on the sides, on the margins of the water bodies, as a way to reduce, through different processes, the chemical loading entering ultimately the water bodies. How do they look in the field? You have a couple examples here. For example, under the tree line here, there is a waterway. You can see a little bit in here. And then you have the field on the sides, the fields. And then you have these bands of planted vegetation, maintained vegetation, which ultimately they can be very effective in controlling the substances from the source, the field, entering the water body. Here's another example, in this case, on a drainage canal in Sweden. This is in Ohio here. And so the idea is you say, well, how complicated can this be? We're talking about grass. I mean, so at the end of the day, I mean, it's just a piece of grass, So let's look into this a little bit more in detail because it's quite surprising. And I want to start motivating the discussion by the words of John Muir. I don't know how many of you are familiar with him. He's a famous naturalist. He's actually the father of the national park system in the US, which actually was the pioneer conservation movement around the world. Many national parks around the world actually follow the example that the US set on conservation of lands through the National Park Service. And John Muir tell us, this is a famous quote, maybe some of you have heard this, when we try to pick out anything by itself, we find it hitched to everything else in the universe. And what John Muir was telling us is that it's a sentence about complexity of the natural system. So why do I bring this up in the context of mitigation, chemical mitigation, in something as simple, or at least seemingly simple, like a buffer, just a grass area? And so let's take a look at the complexity of this system, because there are many components interlinked, which are really interacting dynamically and cannot be separated. And on one side, of course, we have, if you want, we can start with the buffer itself, the grass area, which is vegetative filter strip, VFS, which is of different composition, different species, which of course will be conditioned by the local characteristics, what can grow and what cannot grow. Then we have the crops, of course, which are ultimately, or in other cases, could be other types of source areas. But in this case, we're going to put crops because they are also part of the biological compartment. And there is, of course, a lot of microbiology related to chemical degradation and other things happening. So we have the biological component, which is ultimately dictating the source of the chemicals, the types of chemicals to be used. But then in terms of the mitigation, also the vegetation plays a role on how these are trapped potentially inside. We also have the chemicals, of course, and under physicochemical characteristics, we have the climate, the soil, the hydrology associated with that, and of course the chemicals themselves. You know, do they sort or are mostly dissolved? What is the half-life? How long do they stay in the environment based on degradation characteristics and so on? So the physicochemical compartment is essentially the aggregation or interactions of all these. And then of course we have the sources, which are dictated by humans, the land use, the decisions to use the land for rural, urban, what put on the land based on socioeconomic drivers. So ultimately all these things conflate to create many unknown components and interactions, which ultimately result in what we are going to call emergent behavior, which ultimately is surprises. For much we have tried, we keep having pollution in our waters. And the reason for that is that there are all these things that we cannot really very well account for, that at some point, although we think we understand how things work, at some point they surprise us. This is what we call emergent behavior in the context of complexity science. So in fact, this is a complex system. A thing as seemingly simple as a mitigation of chemicals in a grass area is actually a complex system with many, many components interlinked, each one of them with their own complexities. And ultimately, all this is related to the embedded uncertainty in the system, which is a very important component to consider when trying to understand the natural system, environmental systems, pollution systems, or events like the ones we are trying to go after. So with that motivation, what do we do with complex systems? I mean, do we just throw up our hands and say, well, nothing to do about it? Well, in fact, what we do as engineers is we apply what we call systems thinking, which is a way of taking the whole, breaking it apart into pieces, assigning rules or processes to the pieces, and then try to put it back together to predict the behavior of the system. And once we are able to do that, then we can, at some point, or maybe at some level, predict that behavior and be able to manage or mitigate the risk, perhaps not completely avoid it, but do better than we generate. So models are a central, cornerstone of this strategy, because this systems thinking translates into breaking all these pieces, algorithmic or equations behind those, and ultimately putting them back together. The models allow us to do this management or risk mitigation on these complex systems, and in particular on the pollution control, or what we call mitigation system. Okay, so modeling to understand, reproduce, forecast, control in terms of management and planning the system behavior. All right, so one other thing that we need to recognize before we move any further is that because of the complexity of the system and all the drivers and all the people involved into this process, it's very important to recognize that this is a joint effort, that pollution mitigation requires many people, every one of them with their different contributions, to work together towards ultimately the goal of sustainable production in our context, which is at the bottom here, which is, I hope, what everyone cares about. Ultimately, we realize we need to produce food, fiber, or any other utility from the land, but we want to do it in a way that will be, we can pass on the land and the resources to future generations. So motivated by that, there are a lot of people interacting, academics like us, which develop the understanding, the processes, the tools to simulate these behaviors, minimize this risk. Now, on the other side, of course, we produce models, but also data. And in the context of that, there are also industry, in particular in the field of chemicals, agrochemicals, important industry that, of course, also does their own testing, generates their own data, even at times their own models. And altogether, academics, industry, also producers, which are interested on using these chemicals to ensure the production in the land and ultimately their economic gain. Okay, so you have producers, you have the academics, you have the industry. Then you also have the general public. And if there is one topic that everybody will have an opinion on is pesticides. Just go out there and ask, are you concerned about pesticides? And 99% of the time, people will answer, yes, I'm very worried about it. They probably don't understand the processes and the degree of risk. There might be, there are in fact a lot more other things that are way more dangerous than maybe pesticides, you know. But that is the one thing that everybody has an opinion and awareness on. Okay, and then trying to balance the act. Okay, are the regulation, the policy, regulatory bodies, the agencies, the government, trying to, on one hand, they allow production because it's a service that we need to have to sustain population, food, ultimately. On the other hand, the interest of the industry, which wants to sell, make money. And on the other hand, of course, the science and the best, the transparency in their decisions and so on. And it's a difficult act. And everybody has to work together on this, okay? Just to give you an idea, when I mentioned the agrochemical industry, I don't know if you have an idea how much does it take to fully develop a product from the chemistry to the market at the global level, and I'm talking about, you know, largely used products. Do you have any idea?
1 to 2 decades.
In time, and how about the money?
Many, many millions.
All right, $100 million. Just take that, you know, give or take, $100 million. Okay, so you can imagine the expectations of gains on these products on one side, but also I have to tell you that 80% of that cost is not chemistry, is not production, is not you know, marketing. It's actually the regulatory process. It's producing the burden of proof to show that these chemicals will not be noxious in the use out there. Okay, however, even in spite of all this process and checks, sometimes we find that we have problems, okay? And then we have to mitigate the use. All right, so long introduction to get started. Now, let me just give you an idea of how these simple pieces of grass work, okay? So let's start with this source area. And again, I put here an agricultural field, but realize that it could be other, could be urban. Very important in urban settings, by the way, this practice. So here we have a source area where chemicals have been applied at some point. Agrochemicals are noxious chemicals that could produce effects, unintended effects, on what we call non-target organisms. Non-target organisms are components of the ecosystem that ultimately we don't want to kill. All right, they could be plants, they could be insects, they could be mammals, amphibians, you know, shellfish, whatever. We really don't want to. Those are not the target of these chemicals. The target of the chemicals are the pest, the disease, you know, whatever you're going after. So non-target organisms is the language used here. And what these chemicals, the concern of the chemicals is that they might damage non-target organisms. So we apply the chemical on the field to kill the pest or whatever it matters. Now it should stay there and do what it needs to do. But guess what? Rainfall comes along, and then if there is sufficient rainfall, there is a process that in hydrology we call excess rainfall, which essentially is that there is too much rainfall for it to infiltrate, and then part of that is going to be moving on the surface downwards, you know, down a slope towards the receiving water body. And the problem is that when water runs on the surface, it picks up stuff, dissolved or particulate, because when it goes on, it also runs with sediments. If the soil has been broken, there are loose particles, and those are moved by the sediment. Okay, so let's take a look at this. So what happens then when these chemicals either attach to the sediment, the water, and the chemicals attach or dissolve, move from the edge of the field, right about here, and if there was nothing in between, they would get immediately into the water. But now we put this area of dense vegetation in between. And why do we do that? Well, the first thing is that vegetation increases the hydraulic resistance to flow, but also infiltration. Why? Because the roots are breaking the ground, there is organic matter accumulation, there is soil structure that improves in time, and studies that have done parallel of infiltration in these buffers, once they have been established for a while, and the infiltration in the field, they indicate that there is about an order of magnitude, a factor of 10, in infiltration characteristics on an established buffer with respect to the field. Okay, so there is this increase in soil infiltration, which, by the way, has an immediate effect on the dissolved phase. The runoff gets reduced because it goes down in the ground. Okay, and then you reduce part of the chemical load because it actually gets in the ground as opposed to getting into the water body. But the other part is the resistance to flow. This resistance to flow is quite interesting because, in fact, it delays the velocity of flow. And we know in sediment mechanics, transport of sediments, that the settling of the sediments in the flow, in surface flow, is a function of the velocity. The slower is the flow, the more settling of particles that happen. The first particles to settle, because flow is related to transport capacity, energy. So the moment the flow gets delayed or is slower, particles start settling along the way. The first ones that get settled are the big ones, okay? And then as the velocity is going down, finer and finer particles get settled. Some of them never get settled. They are actually buoyant. They just stayed up. But you know, a good number of them get settled down. So the fact that the velocity gets delayed or reduced because of the roughness of the vegetation increases significantly the settling of the sediment, and therefore the solid phase of the chemical. Okay, so together then we have a reduction of the pesticide or the chemical, the agrochemical, either because it gets infiltrated if it was dissolved, or it gets settled if it was attached to the sediment. And ultimately, only a fraction of that gets into the water body. And I'll show you to what extent, what percentages of reduction we should expect with a well-maintained filter in a minute. So, one very interesting point I want to make in here is that when we face many of these management decisions, we can take different approaches. On the top here, I have what I call political design, which is somebody somewhere makes a decision that we need to implement a practice. For example, these buffers, these VFS, vegetative filter strips. Political design means, hey, somebody has said they are good, everybody uses the VFS, and they have to put them in the field, and it's 20 meters, okay? Or 10 meters, for example. The next step in that decision is making it a little bit more transparent, and you can see this line here, which increases transparency in the process. But conversely, on the other side, opposite to that is the simplicity. So the most simple is when somebody says, we must do it, no explanations given. Very little transparency, but very simple. We go down the ladder because, of course, at times we need to, adapt a little bit to different conditions, and then we go to fixed coefficients or empirical relationships. So a few studies are done, and we get some sort of reduction, expected reduction based on some conditions, some maybe empirical fitting of some limited data, and then with that empirical equation, we do a little bit of sizing, or what is the type of buffer that we need to place, where. But the problem with these things is that they are derived from data, and we know in statistics that empirical relationships are limited to the data range, beyond which we cannot predict. And the problem is that this is a complex system. I already showed you before. There are lots and lots of different factors that conflate to ultimately dictate the efficiency of the buffers or the sizing and characteristics of these buffers. So it's very hard to really propose fixed coefficients to a complex problem. The next thing is what we're going to call quantitative mitigation, which ultimately requires the use of a dynamic, mechanistic approach to understand the coupling of all these components to determine the fate. And I have to tell you that grass buffers, vegetative filter strips, have gone through this whole process in time, to the point that early on, the first time that they were used was in the biggest and most known, probably the first one historically that was brought to the general public attention, which was the Chesapeake Bay degradation, disaster, which, by the way, we haven't been able to solve. I mean, the shellfish or the fishermen at the end of the Chesapeake Bay, they are still suffering from low productivity and polluted product because all the large surrounding area, the Chesapeake Bay, there is a lot of cities, a lot of agriculture, that they are ultimately still, even today, after everything we've done, we're talking about the 60s, okay, we haven't been able to solve. So at that time, the governor of Virginia, this was roughly in the 70s, they said, well, because we have some evidence that buffers work, everybody must put around the lake these buffers. And of course, that was a pushback because, you have to set land out of production. What the hell do you do? There is a cost to that, And of course, immediately when there was the pushback, because the governor just said that based on very limited evidence, there was a need to refine. And that's when empirical approaches came along. But these empirical approaches, when the stakes were going up, and remember, the original problem in the Chesapeake Bay were not complex pesticides. They were actually nitrogen, okay, or phosphorus, nutrients, which is a simpler problem to some extent. But when it came down to the pesticides, which are high stakes, they could be very toxic, then there was a process by which the different stakeholders kept proposing fixed political design one size, then the fixed coefficients, and ultimately they had to understand that the only way to really come about is really dynamic modeling, which is where we come into the picture. Okay, so remember Occam's principle. I put it down here. Does anybody know who William de Ockham was? Okay, he's a philosopher in the Middle Ages. Okay, and he's famous for the double sword, Occam's sword. I don't know if you heard that, but essentially he proposed that nature is wise, is infinitely wise. God is behind nature. That was the time. Okay, if God is infinitely wise, how could he make anything in nature to be wasteful? So in the presence of two alternative explanations, the simplest one must be true. And that was a belief which wasn't trained in a religious belief as well, but ultimately has inspired science along the way. So simpler is always better, but careful only if it works. Okay, we have to make sure that that works. So in this process that I have talked about, simplest could be the best, but only if it works. And we are at the case here where we need to go down into this ladder for more transparency and more complication. All right, so let's review this idea. So how effective could be these buffers to reduce runoff pesticides from fields? And this is a survey, a paper that was published by a good friend of mine, Stefan. And what they did is they swept the literature at this time. They just republished a 2019 revision with new data sets. But at the time, what they did is they plotted for all these studies that they had been able to collect, 200 and some, I don't remember, a lot of studies. They plotted the efficiencies that had been reported from these buffers through experiments. How much of the runoff was of the chemical was reduced, the load, the mass of the chemical was reduced from the edge of the field to the other side of the buffer, sampling before and after, what was the reduction. And they plotted all the data and look at what they got. The x-axis here is the size of the buffer. This buffer strip width is from the edge of the field to the water. How much land you have to dedicate to the buffer. If you multiply by 3, you roughly have feet here. Okay, so 10 about 30 feet, just to give you an idea. And on the y-axis, you have the percentage reduction. And now you can see that you could say, well, bigger is better. Okay, I mean, large buffer stands to reason that will be the most effective reducing this runoff. And now what you find is that indeed at any given length, you get about the same expected reduction. Why? Because we are lumping data from many different cases, and so you're losing a little bit of what's driving what where. But across the board, it's important to recognize that the single predictor of efficiency, Y, is the reduction of pesticide. 100% would be no pesticides go by. 0% is all the pesticide goes through to the water. Okay, so it's clear that the buffer size is insensitive. So that there are other factors that must be driving this huge range of expected reductions, which are in fact the hydrology, sedimentology, and pesticide characteristics, the processes. Okay, where infiltration, the reduction in flow, followed by sedimentation, as we expected, the two phases, whatever happens to those two phases, ultimately dictate the reduction. So the range, the observed range is from 0 to 100%, which is to say, how effective is a grass buffer? From 0 to 100%. You can imagine, I actually had to give this answer once to an agency that they were coming for a fixed number to assign to these buffers. And I said, look, from 0 to 100%, which is not very satisfying. I realize that. Okay. However, on the long term, greater than 50% can be expected. These are the medians that you see here. Okay, all above the 50% line. So they are effective. They are actually surprisingly effective in reducing these chemicals. And if you get a 50-60% reduction of the chemical from what it was before you put the buffer, that's really worth consideration. Okay. All right. So the processes then, just to recap, are we have from the source area on this side here, you have the pesticide or agrochemical source. And by the way, not only pesticides, this could be nitrogen, different forms, ammonia or nitrate, phosphorus, So depending on the characteristics, it could be sorbed or dissolved coming from the field. So this is all dictated by the field practices. When did you apply? When did it rain? Did you cultivate it? Was the soil ready to be transported or not? What is the size of the soil, the particle size? Small, large, will they settle, will they not? I mean, you can just follow the process, okay? So the chemical comes distributed into the liquid and the sediment phase, enters the buffer, starts hitting the vegetation, reducing roughness, ultimately infiltration because it's higher here, and then part of that goes down into infiltration, part of that gets settled, and then ultimately part of that, hopefully a small amount, gets out. And we need to understand that all this then is driven by the water phase, the runoff, which is dictated by the rain, the infiltration characteristics, okay? And ultimately the settling of the sediment and other processes, including the chemical characteristics. So then you have attached to the water, which is the energy, ultimately, the sediment settling, and from there, the pesticide. And all these processes together have to be interacting dynamically to get the result. So I had the pleasure of giving this talk at the International UIPAC meeting, which is the International Chemistry meeting in Australia years ago, chemists, okay? And my talk is not about chemistry. Well, I put just chemistry, okay? Because the problem is that we need to understand the fate and transport of these, So let me put it this way. A bowl full of mercury is not toxic unless you go to the shell, open it, and drink it. And that going to the shell and open it and drink it is what we call the exposure, okay? Where the effect is the intrinsic toxicity of the mercury, which is very high. But if the fate and transport process, the idiot that goes to the shelf and drink it, is not in place, it doesn't matter how toxic the product is. So this fate and transport, the water, the sediment, together with the intrinsic characteristics, effects of the chemical, need to be considered together. So it's not just about chemistry. And many of the solutions that we see out there for screening and so on are only based on the chemistry of the product. This is a very incomplete way of attacking this problem. Why do we always look at the chemical or the characteristics of the product first? Because this is very complicated. This is the story of the water and sediment is not to the reach of everyone. It is to us, our group, okay, but not many other people. So we need to continuously communicate that you must consider all these processes. Unless you do this, you will not be able to get any prediction capacity on these processes. So VFSMOD, the vegetative filter stream model, was developed many years ago now. It was like you guys, when you're sitting, it was my PhD product, okay? And of course, it has been improved and developed over the years by many other PhDs like you, okay? And a lot of work and support from many agencies. And so ultimately, this is the model. The model is essentially this one that I just presented here. And it has these three components, which are numerical, mathematical components. The overland flow equation is solved by a finite element solution of the overland flow equations. It's coupled to physical infiltration components, mechanics of sediment, and ultimately all the chemistry that we mentioned, attachment, detachment, degradation, and so on. So all these things from the source area, they are input into the model. The model then does the water through the overland flow component that ultimately responds to a hyetograph, or essentially a dynamic rainfall, okay, pattern during the event, the short run event. The interaction between the rainfall and the infiltration determines how much water keeps moving on the surface in every node of the finite element mesh. And then once we solve the flow field, then we couple that with the sedimentation mechanics. And then ultimately, on the basis of that, we can determine by mass balance the amount of chemical that is settled or infiltrated, and ultimately how much of that goes ultimately out. Interesting is that the model has two infiltration components, which prove very important, particularly from where Professor Darnault is, and I will tell you in a minute, okay? Which is one that is just deep infiltration, the other one is actually infiltration under shallow water table conditions. So if you have, seasonally, a water table that is very close to the surface, that limits infiltration and has a cascading effect on how everything moves around. More water, actually, because less water can infiltrate, more water moves on the surface. Because more water moves on the surface, more sediment gets transported, more flow, less sedimentation, more sediment, and therefore more water, more solid phase move, and then more chemical moves out. and then the reduction of the that happens in the filter gets reduced, so the effectiveness of the VFS gets down. Okay. All right. So this is just the finite element solution. Nodes across, rainfall on top, incoming hydrograph, outgoing hydrograph, delay, reduce, source areas characteristics, roughness, and infiltration characteristics along the path. Blah blah blah. You know, all these things. These equations get all work together. And the infiltration component, again, two of these. One of them is this one that I'm talking about. So you have a shallow water table perched here, you know, a seasonal shallow water table. You can actually limit the infiltration, which is what we did here on this new algorithm that we developed a couple of years ago. And when I first, I did this while I was on a sabbatical in Lyon that we were talking about in France, because here in the US, buffers typically are an upland management practice. So not usually you have an impeding condition where you have a shallower table, but at times you do always as well, particularly as you go to the southern part of the US, but you know, in the other parts of the US, it's not so common. But anyways, I didn't think that this was gonna be an important factor compared to the others, okay? Compared particularly to the flow, sediment, you know, all the things that we've been discussing, rainfall and so on. But here we are. I said, well, you know, if you guys are interested in doing this, I was there for a year. I was working for the French government, you know, they wanted to know about this. And I said, what the hell? This seems like an interesting thing to work on. So we developed this physical component that actually does a limitation of infiltration based on this initial hydrostatic condition with the soil water. I mean, with the shallow water table. Okay. All right. So what does it mean? Well, once we developed this algorithm, there was actually some laboratory testing. So this is a large soil box. This is the grass growing on the top. And then we had a siphon, a communicating vessel system that we could control the water table in this box so that we could get water and chemicals on the one side. And then we could control the rate at which those overland flow, if you want, was coming on top on the side of the buffer with the slope. And then we could monitor how much of that was actually coming down as the water table was in different positions and ultimately see if the model could work. So the model with this new component, I don't know if you can see here, but there is the VFSMOD is the thin line, the dashed line is the measured outflow, the inflow is actually a square hydrograph. Okay, so these are actual hydrographs measured. So whenever the two lines are right directly on top of, so for example, in this case, so the first two on the top is free drainage, so the water table was not present in the soil, it was just runoff on top. And then the second pair of studies was with the water table perch, somewhere in the middle of this box. What was the effect? And you can see comparison of the top and bottom is that the water table actually it makes at some point the soil saturates and then the inflow and outflow are the same. So the two inflow outflow curves are on top of each other, which you would expect. So there is a limitation of the infiltration capacity and there is more runoff on the surface as we expected. And then these two lines that you see almost on top of each other here, you know, they separate a little bit here, but they go together. There's a little bit of delay, but they go together and then they go together here. This is how the model predicts with respect to the observation, so very close. So the physics of the model work for shallow water table. Then we went and applied to two locations with limited data in France. One of them was in Jaguar, which is the silty, loam soils, very waterlogged soils for cereal production, and then in Morsil in the Rhone Valley wine production, slopy lands, more sandy loam type of soils, and we just checked the effect that could have. So this the line, the big line here, the dark line here is the incoming flow, two events to measure runoff events. And then what we see as the dashed lines, different types of dashed lines are the effect, the measure with the symbols, or the simulated outflow from the buffers, okay, as you move the water table up and down, you know, in these fields. And what you can see is that indeed, when the water table is very near the surface, 0.4 meters, for example, in this case, you almost get the same amount coming in and out of the buffer, meaning that there is almost no infiltration. When the water table is very deep, like 2.5 meters, then you get a very small amount of runoff coming out, which is what we would expect. So physically, we can predict the field behavior that we observe in this case. And if you put it all together, we did a little bit of a sensitivity analysis, but just to summarize what we are to expect, 0 in this graph, water table depth, means that the water table is right on the surface. And then as you move down, deeper into the soil, you get other depths. Okay, so this will be a deeper water table, 1.5 to 2 meters. This is just on the surface. And on the y-axis, we have the expected reductions of pesticide flow, Q, E is erosion sediment, and P is the pesticide. So the first two lines that we see here is for the two sides that I just presented to you. You can see how the reduction in runoff, DQ, these two lines that are on the bottom, go from almost no reduction, 0% reduction, right here, to about between 80 to around 80% with the deeper water table. So big sensitivity to the position of the water table in reduction of runoff like you would expect. In turn, there is a little bit of a slope here. You cannot see very well because the particles were fairly coarse. But anyways, there is a little bit of a sensitivity to sediment, not much, almost nothing. And then ultimately, however, the dissolved fraction of these chemicals were matching the reduction in flow, and therefore there was also a sensitivity to the reduction of the pesticides. So these three lines here are 3 pesticides used in the area. And you can see that it goes roughly from 50% to close to 100%, depending on where the water table was. So indeed, contrary to my expectations, the water table, the seasonally present water table, could indeed limit the function of these buffers. Very important to realize that. Now, to move on along the processes, and just very quickly, in terms of sedimentation mechanics, I have to just remind you that when we talk about how sediments move on the surface, we separate typically the particles in 2 classes, what we call coarse particles. They're very heavy, and the way they mostly move is a bed load. Bed load meaning rolling, they roll. Okay, they are pushed by the water and they keep rolling down. They're too heavy to really be suspended. And then there are the fine particles which get suspended. And the fine particles get suspended and settle in trajectories, like shooting, like a cannon shooting on top, depending on the velocity of the flow, transport capacity that we mentioned, but also other factors like, of course, the setting of those particles as dictated by simply buoyancy, okay? Stokes law that we call, okay, and ultimately the turbulence of the flow, which could keep them afloat, because the turbulence could be pushing them up at some point. So the turbulence of the flow, the sedimentation characteristics of the particle, and the velocity of flow will determine the setting of these fine particles. All right, so those 2 classes are modeled independently. The bed load transport is actually modeled using Einstein Jr., the son, okay, not the father. And I don't know if you know the quote, a talk between father and son, Albert Einstein, the physicist, Nobel Prize, and the son working on sediment. And the father is telling to the son, the physicist telling to the son, I don't know how you can work in such a difficult problem, okay, which is sedimentation. So on the other hand, we have the suspended particle, which is this equation that you see here that was developed specific to grass buffers by the Kentucky group in the 70s, Tollner's equation, which essentially, as you can see here, the difference in sediment load between entering and exiting the buffer is related to the Reynolds number, the turbulence, the velocity of fall, which is the sedimentation characteristics of the particle, and also the velocity of flow, like we would expect. Okay, all right. So with all that, then we can actually settle the differentially the particles across the filter, coarse, fine, and ultimately determine how much of them or how many of them go out, or if you want, how much of the sediment actually gets out of the buffer, how much of that gets trapped. And then we'll see now, considering the solid phase, which is the sediment, the infiltration that happened or the reduction in flow. Now we look at pesticides. And of course, now that we have the 2 phases and the dynamics of those 2 phases, we can distribute the chemical across those 2 phases and mass balance the amount that comes in that was initially dissolved or solved or attached to the sediment, how much of that now gets settled or infiltrated, and how much of that, finally, how much load gets out of the buffer. So these are the processes. We have the entering, sediment and runoff, we have precipitation infiltration, and we have the runoff coming out. And now we have the chemical characteristics that do the distribution between those 2 phases. And ultimately, mass balancing this, we can get to the ultimate prediction of the reduction of the pesticide or the chemical, because this equation is generalizable to other chemicals. And initially, in 2009, Sabah, with a group of researchers, proposed an equation which was a function of reduction in flow reduction in sediment, and chemical characteristics, where FPH is the distribution coefficient of the pesticide. Okay, so the sorption of the chemical. And also the percentage of clay in the, because clay has a large sorption capacity, and if there is a salt clay on the moving water, you have an additional phase to consider. Okay, so this is an empirical equation. It was successful with the existing database, which was limited. You can see this in here, to predict the reduction of sediment on the basis of these two components. By the way, when these people developed the equation, they didn't know about VFSMOD. But then they called me up one day, and then they say, hey, Rafa, we read your papers on VFSMOD, and of course, for our equation, we need predictions of the reduction of flow, predictions of the reduction of sediment, so that we can apply our equation to predict pesticide, which is a high stakes game, both for the chemical industry. By the way, Savard worked for Bayer, the chemical company, the German chemical company, and there were people from EPA, you know, the Environmental Protection Agency, and other companies involved into this work. So they said, sure, and then I coded the equation, and then they tested it, and I'll show you the results in a minute. Now, in time, it was found that, of course, with a limited database, you could find instances where these predictions were not as good as expected, simply because as more studies were considered, the initial conditions of the fitting were not considered, and therefore you need to extend the base of that empirical equation. So they recalibrated in 2018, Stefan, with 244 data points, increasing the database significantly. They extended the base and improved the prediction capacity of this empirical equation. However, as it happens often, people will question the empirism, just the fitting. You know, is it really generalizable? Can we really use an empirical relationship as opposed to a mechanistic, meaning physical processes? Okay, and then they also propose a mass balance. The mass balance essentially is the, again, liquid phase, solid phase, how much chemical is in each one of the phases, and ultimately on the base of that, how much gets settled and how much gets out. This is the last equation. And notice that the nice thing about this equation is that it has 0 regression coefficients, okay? Versus the Savard recalibrated, which was the best standard, you know, the good prediction. And here is on the x-axis is the measured pesticide reduction on many studies that I mentioned before, and these are the predicted on the basis of the model, okay, with each one of these equations. And what we can see here is that the Savard recalibrated, which essentially was forced to meet the data, had an R-square or a Nash, in this case, because it's a nonlinear R-square, a Nash Shipley coefficient of 0.82, which is very high across all these studies, okay? Now, you can see different symbols here. The new Savard is the red, so the reds aligning on the bounds of uncertainty here, or prediction uncertainty, are the good predictions of the model, 82%, or basically Nash of 0.82. And then the mass balance equation didn't do too bad, considering that it has no regression parameters. So partitioning between liquid and solid phases and mass balancing the mass of the pesticide, how much stayed in, how much got out, gave a prediction which was not too bad, 0.874, and avoid the empirism of the empirical equation. Okay, so with that, then we have now a solution to potentially use in the regulatory process where there won't be questions about the empirism. Or if you want to refine, you can also use this one. So all these equations are built into the model. One important question about these prediction strategies for pesticide reduction in buffers for the mitigation is, do they work across all chemicals? And the distinct characteristic that we have to keep in mind is the sorption capacity. Remember, we talked about that, how much of the chemical naturally attaches to the sediment or is dissolved. Okay, that's what we call KOC, or the organic carbon distribution coefficient, which is essentially sorption coefficient. Okay, so what they did is they separated the large data set that you see here, and they went for what is considered to be low sorption, the one on the left, and high sorption. And they were trying to see if indeed the good prediction that was used on the overall data set was also maintained for high and low sorption products. And indeed, the prediction was also maintained across. So it was quite promising that the equation could be used with generality, both the refined empirical, but also the mass balance. And interestingly enough, by the way, you can see that the prediction of the second equation, which is the mass balance, is a little bit better for high sorption than the other one. Okay? All right, so now we have an equation we can predict, and now we can move into the regulatory context. Okay? One more thing about processes, which I think is very important, which is a typical question. And now I have to also tell you, because you are going to be academics, scientists, that the regulatory environment, the people that are going to make use of this for policy, but also the chemical or the industry or the economic interest, do not necessarily want to know about the worst that is coming to them. They just want to do, limit their portfolio, their focus to what's really relevant now. So that essentially is related to the question of, okay, great, we can sink part of the chemical, it doesn't get into the water, we then limit the effect on the water. And by the way, all this is down on the regulatory context. There are models that do the transport and generation of sediment, water, and pesticides on the field. There is an Environmental Protection Agency model, PRISM, that does all this part in here. There are models that do the water body dynamics, settling, and degradation in the water column. Exams, VM, also EPA models. And now there is our model in between to do all these things, okay? So ultimately, the important outcome of this analysis is the concentration in water, because that's where the non-target organisms are, amphibians, larvae, things like that. So what they do on this analysis, model analysis, is daily, numerically, they calculate the concentration of water, and they look at if it exceeds a threshold for different indicator organisms, okay? So the focus is in here. So granted that by putting the grass buffer, we could obtain a high reduction of the chemical that otherwise would be coming from the field directly into the water by the use of the buffers. And now the next question, and by that, essentially reducing the concentrations in water and limiting the impact. But now I think a good question is, and what the hell happens to the pesticide once it gets into the buffer? Is it the end of the story, or there is more? And this is where, I raised this question, and then of course they shut me up. They say, oh, we don't want to know about that. They said, well, okay, that's fine. But and now back to the roles that everybody has to play, academics have to anticipate the questions, the next generation of questions. We need to be necessarily ahead of the game, okay? And this is one of the questions that we wanted to anticipate. And sure enough, now we're in the middle of a fight. What happens to the pesticide once it's reduced, okay? So we developed this pool. We are still developing. I have now a new project that I will start with funding from the industry to essentially try to validate the equations that we put together, where we essentially track, we said before, we get a total mass retained in the filter, which is of course in the liquid phase and the sediment phase, in these two components here. Of the liquid phase, there is deep infiltration that goes to the subsurface beyond the reach of the surface, but there is also pore water right on the surface of the ground that could interact with the next runoff event in the series. Okay, and part of that could dissolve and go back into the runoff. So this fraction of the subsurface infiltrated water could also be active for remobilization, or later on coming up again. And then of course the sediment amount stays on the surface. So every one of these fractions, the sediment on the surface and the pore water on the surface, dissolved and absorbed, they go through degradation on daily time steps that are also, these are general degradation equations, exponential decay equations that are modified by temperature and moisture content in the soil, because the biological degradation is affected by these two factors. And then you have daily time steps until you get to the end mass before the next runoff event in the series. And then when the next runoff event comes, so many days after the previous one, then the mass is redistributed again between the pore and the solid phase. And then parts of that actually make it back into the surface to contribute potentially to the processes of, again, infiltration, settling, and so on. So we do a full cycle of where the mass is. And by doing that continuously, part of the mass gets resuspended and remobilized, so adds to the expected mass. Out here, part of that actually gets just sunk and below the reach of the surface. Okay? All right, and there are a lot of these references, and I gave Dr. Darnault the slides, so you can actually, if any of you is interested, you can go back and read some of these papers. All right, and now you might be questioning, okay, so this is all great, a lot of complicated details, a lot of equations and so on. And now the question is, can we test these models? And the issue of model evaluation and testing is critical. It's humongous. I mean, it's a huge, huge problem, okay? I actually teach, we have at the University of Florida a graduate certificate in biological systems modeling. It's a 4 sequence of, we teach from coding to evaluating models to running them in high performance computing settings, and many, many things with them. But one of the components I teach in that course is precisely model evaluation, because we have to be very rigorous about to be able to understand if the model is really representative of reality. Because you all need to remember that a model is nothing but an abstraction of reality. And by abstraction, I mean simplification. So whatever we put on paper in terms of equations is never the full reality. And regardless of the physics and the mechanistic approaches and everything we believe so dearly on, there are a lot of uncertainties in how we parameterize these physical equations. There are a lot of things that are lost in translation that we need to be very aware to understand what is the impact ultimately on the predictions we want to make. And we might have the most sophisticated and beautiful model in the world, and at the end of the day, when we apply, we don't get good results. And it's not because the physics are wrong. It's because the things we feed into the model might not be so good or so easily to parameterize. It's the famous aphorism that we use in modeling, which is garbage in, garbage out. Okay, so that we have that problem. All right, so how do we, how can we make sure that this complicated thing that I presented to you, VFSMOD, actually works? And of course, it starts with field data. And you know, the cry for field data is always there. We will never have enough data. But luckily, a lot of people, because of the high stakes question of runoff mitigation and the importance it has to either sales of chemicals or production of food on the other end, and of course, the awareness of the general public, you know, there is a lot of interest on getting tools that are predictive and, you know, robust. And that's why a lot of studies have been done. Most of them, interestingly enough, by industry, because they have to do those as part of the assessments, the regulatory process. So they have their own database of a lot of these studies. So by mining these studies and compiling the data, we can actually validate the models. And part of the validation I already presented to you are those one-to-one lines that I showed you before. So there is good data for validation. Here is just the early database that I mentioned before, revision of that database and how they distribute in terms of the reductions of pesticide that the data set contains. So for different studies, if there was a high or low reduction of pesticides, according to the characteristics of the buffers, okay, the filter strips, different vegetations, different types of densities, slopes, you know, conditions associated with the soil types and the rainfall characteristics, land uses, inflows of sediment or pesticide, you know, many things are included into these ranges. But it's nice to see that there is a good representation of low to high reductions. So it is useful for testing, because we don't want a limited data set with just very narrow range. You know, we want to have the full gamut so we can actually stress test the models to see if they do well. Interestingly enough, the revisions of the data sets are increasing, the characteristics change somewhat. Here is a plot of the frequency of these reductions. These are the percentile, sorry, these are the reductions. You can see that there is a slight difference. So on the 50th, which is the median value, you can get to, on the early data set, 60%, later on 76%. So as more studies are added, there seems to be a bias in the median. But important thing to remember then is that we have a broad data set. Also, if you partition the existing studies on the later of the data sets between low and high sorption, because again, we want to make sure not only that there is a good representative range of reductions, but also if there are enough low sorption and high sorption pesticides in the database, so we can actually stress test the model to see if it works. And there is representation of both groups with the different efficiencies and so on. So the data set is quite rich. So that was used for this comparison I did. I presented this. This is essentially the data set, so we can actually test the efficiency of the model for that. And another thing that is very interesting is what we call in modeling, the most brutal test that you can actually do is what we call cold testing, which means a group of modelers get into H1 with their own model, are given a set of inputs. They don't know what the output is. And then they are let, you know, to go for a while, and then they say, okay, you have to come back to the table. Tell me what you predicted. And then they open the envelope and they say, this is the right value. What did you get? Okay, that's called cold testing. All right, so they did this cold testing exercise and calibrated model with the contenders. The contenders were a suite of models. You might recognize some of these ones. Essentially, a suite of models that somebody have come to the EPA. This was commissioned by the Environmental Protection Agency. That they had pesticide reduction capability for buffers. So they came with all these models to the table, and then they said, okay, great, let's use these models. We'll give you the same data set, and the same data set was these places, Georgia in the US and Iowa, two different farming systems, and then also in Europe, this Germany data set with different pesticides, different conditions, blah, blah, blah. And then they ran the models and brought back the results, and then they calculated for each one of the pesticide, runoff, and sediment, the mean standard error, or if you want, how far the model, mean absolute error, how far the model deviates from the true value. And you can see that VFSMOD came up very nice on this comparison because it had a much lower, so only 8.5% error, which is surprising. I was not related to this exercise. I saw the analysis later because they don't want the developers to be involved into this, okay? So a very small error for pesticide and also runoff incident compared to the other ones, which could be in excess of 30%, at times. So from that comparison, it became apparent to the agencies that the model was usable for the regulatory process, okay? And there is lots and lots of other data analysis. I give you a link, and there is also one at the end of the slides where studies have been conducted to test across the world the efficiency of the model against the field data. So that is to essentially support that we can use it in high-tier assessments, which is the regulatory process. So I will just finish with this in the next 5 minutes. And the setting is the following. So now we have this practice that could reduce pesticide runoff pollution. And now the question is, how do you translate that or integrate that into the regulatory process? And this by no means is a simple question. Because one thing is what we do in our world, you know, the academics with our tools and our data and all these things. And the other thing is what people really want to do in the simplest of all terms for ultimately translating these into farmer use or inspection or things like that. It has to be simple solutions that, yes, might be informed by very complicated processes, but ultimately it really boils down to the label. You buy a bottle of the pesticide, there is right in there. A label in the context of pesticide is a legal binding document. So you have to use the pesticide according to the instructions, because otherwise there is legal responsibility on the misuse. So if later on there is a pollution event, massive fish kill, for example, something like that, if you didn't apply it according to the label, you're responsible. Okay, so very important to follow the label instructions. So in some instances, buffers are in the requirements of the use, and they have to be implemented in the field. Unfortunately, when buffers are part of the requirements of application, so you shall have a grass buffer attached to your field of a certain characteristics and so on, many often the way these were developed were empirically, heuristically. So what do we know? Well, 30 feet, just put it 30 feet, but there was no real prediction assigned to that. And that's where we are now moving into the next phase. Can we quantitatively assess the size and composition of these buffers? And where does the model play a role into this? And this is a discussion that has been going on for 10 years, okay? With different levels of success. I'll show you in a minute. It has already been adopted in some regulatory contexts. We are working with the larger of these regulatory contexts, which is the US EPA in the US, of all places. Okay, Canada is already adopted it. California has said, the hell with the EPA, if they don't want to do it, we are going to do it, and they have it on their regulation. Remember, the states can set higher standards than the regulatory level. So they are more restrictive, more refined, so they can do that because it's above the regulatory standard, which at this point is they don't require buffers. Okay, all right. So it's important to have realistic, transparent, and ultimately that they are easy to implement. Okay, those are big things. Just to give you an idea, sequence of models. These are the existing EPA, or also Focus. Focus is the equivalent regulatory environment in the European Union. Okay, it's part of EFSA, which is the European Food Safety Agency, like EPA is in the US, and they also have a parallel. The same models are used in both Europe and North America. Okay, so typically they run the field with this model prism, and then they do the assessment on the water column as the sediments and chemicals enter in the water column over time. They get essentially settled, degraded, blah, 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 and then ultimately they numerically sample daily the concentrations, and then they look at the probability distributions of those, and then they set a threshold for effects, you know, different organisms, how much they can really take, and then if they're above, then they discard the chemical at different levels, okay? So the idea was precisely to build the model in the middle of this process, to be able to use it in the sequence of simulations that are already part of the regulatory process to whenever you reach it, by the way, I should say that the way that these things are done, let me just show you a slide. I think I have a slide here. Yes. So the way that these things are done is what they call steps or tiers. So they start with step 1, which is simply the simplest of the assessments, which is screening. And typically the concentration that is going to be coming out from that is going to be very high, probably unrealistic, okay? So it's basically saying, compared to water, does the chemical pose risk? And most chemicals will be, yeah, compared to water, it will be risky, okay? Then they go into the second tier, which is refined, and they do a little bit better. And then they keep going into higher assessments to refine, add additional evidence, more description, more biology, more chemistry, physics, and so on. And the last one in Europe is called step 4, which is where mitigation comes into place, or in the US is step 3, or basically the higher tier assessment. And that, for example, in here you can see the interface of the European model. When you get into step 4, and you have this model, it's called SWAN, you have an option for mitigation. I don't know, you can read it, but essentially you can, option 1 is fixed reduction coefficients, empirical coefficients, which have their limitations, and then also using the model, okay, VFSMOD. So with that, you can actually select the size of the buffer from the edge of the field. Then you run your simulations, and then you compare before and after how much water and how much chemical was coming without the buffer, with the buffer, and then you see if you can actually meet those thresholds of concern for different organisms. Okay. All right. So because we are finishing, let me just wrap up in here with the importance of field maintenance of buffers. Okay. Because again, when we do numerical abstraction or models, we idealize the world and we say, okay, the best possible settling and sedimentation and infiltration is when the water moves uniformly on the surface, nice vegetation that is, intersecting the sediment, the water, and the chemical associated with that, and that is the highest. That's ideal conditions. But there are a lot of other things that could happen in the field where your vegetation is not as uniform as you would want it, or where you have some sort of other problem that we mentioned with the shallower table and so on. And the issue of vegetation and the quality of the vegetation is very important. So naturally, vegetation don't grow like a lawn. Okay, lawns, are very rare in nature. I mean, there are prairies, but they also have patches within the prairies and things like that. So to really maintain vegetation very, very close, you have to mow it. I mean, that's what we do in the lawns out there in my house. The lawns essentially are maintained close by continuously mowing. These types of vegetation tend to grow together when you mow them regularly. The second very important thing is you cannot apply any chemicals to those buffers, okay? Because otherwise you will deny the effect of sinking. You're adding more chemicals, or what the hell. And then you need to realize that every so often there will be a big event. That return period. Every 10 years we say on this field. If you get the largest event in 10 years, you will get a lot of sediment, you will get a lot of water, and probably you will cover part of your buffer at least with sediment. It will just be inundated. So you just need to know that you need to, every so often, you need to expect to reset the buffer, which means you're gonna level it, so plow it, level it, and then reseed it, let it grow, and then reestablish it. And this is a cycle of about 5 years. Then you're gonna have to mow to maintain it at the perfect, our nominal conditions. Because if you don't do it, there are these studies that indicate that not maintained buffers in time degrade and lose efficiency. Not surprising. So basically what's going to happen is that if you just put the vegetation and you don't maintain it, it's going to be like everything else, it's going to break, and then you don't have the credit or the expected efficiency that you would assign to the buffer as if you were to maintain it. And maintenance includes resetting, et cetera, which I have here if you want to look at these slides later. So very important to end with the idea that we need to not only design properly, and by that I mean the type of vegetation, the size for a particular set of conditions, to ensure a certain reduction that you must have to be able to mitigate the chemical impacts, but you also need to maintain that practice in the field. And that is a big, big problem because farmers, people in general have their own ways of doing things, and they are not necessarily maintaining the nominal conditions. So just this week, we are in the middle of the second North American vegetative filter strip workshop, which is organized from North Carolina. And we have representatives of all these stakeholders, including us, academics. I gave the keynote just Monday to the meeting, essentially to how to, the first meeting was about what are the tools and what are the containers and how we can do this thing and incorporate buffers into the regulatory process. The conclusions of the previous year were that we have a tool, which is the model, and now we need to figure out how to do it. And then also other regulatory environments, California and Canada, and we're going to take a first step into incorporating that into the regulatory process. This year, they're reporting their findings, how it's working. They're going to move to the final implementation, and they have different proposals on how we can actually make it into the hands of the farmers. How do we ultimately translate all these things into a workable, simple enough set of rules that the farmers can follow? And also, there is a win-win for farmers as well into this process. Okay, the win-win could be through financial support programs, partial funding of the practice and maintenance. It could also be environmental credits. It could be also, in Florida, for example, we have this concept of presumption of compliance, which means that if you did what you were told to do, if there is an event, a pollution event later, you are exempt from responsibility. So there are a lot of ideas on the table on how farmers are enticed to adopt these practices, and then how can they get credit from doing so, financial or legal credit from them. Okay, so that's it. One final thought is that the important question then for us, and I think this question could possibly be translated to every one of the fields of study that you guys have, is not if something works. That question is not really very interesting. But really, what are the factors that control, in this particular case, the mitigation of buffers under different conditions? So what are the processes and the relative importance of those that ultimately condition the outcome of the system? That is a much richer question than just do they work. Because the good and do they work is J and A, maybe, but not much attached to that. But if you go into process, you can do a lot more. So the important question is what factors, and I left this slide. These are many studies that have looked at common factors like hydrology, sediment, vegetation, the relative importance and their different settings. Surface channelization, or essentially you don't maintain the vegetation, water runs through. You lose efficiency. Here are a few publications that indicate the potential loss of efficiency. Also, the chemical application in the field matters for efficiency of the buffer. Shallow water table, we talk about that. What happens to their long-term trapping of the pesticides, the residues, degradation, others. We just finished a dissertation in the department on soil preferential flow. So we're talking about macro pore flow, in the soil. Could they actually be a bit important in areas that are particularly susceptible to preferential flow, which happen to be at the interface of the river and the land? Because these areas are very dynamic. There is a lot of biological activity, roots, gradients of flow. These things develop pipes and macro pore flows. They're very hot spots of macro pore. And therefore, if those indeed are there, and we put this practice right on top, how much of the efficiency could be lost to the macro pore flow? That's the context of this one. And very interesting results as well. Okay, so in conclusions, we need, for all these problems which are complex in nature, and every pollution problem is complex in nature and exhibits emergent behavior, meaning that surprises are on the way. And in fact, our ability to tackle these problems is limited to the extent that the problem is very complex, okay? So understanding that pollution is complex, and that's why we haven't been really able to get rid of it. And by the way, any of you that has a call into pollution mitigation or just simply understanding water pollution is going to have a job forever, okay? So this is one topic that is not going to go away. So if you guys are choosing to go into this line of work, you're going to have work forever, okay? Because we are still not able to do this in spite of our advancements. So we need to do a system-wide assessment of the important factors that control, in this particular case, the pesticide mitigation. And this is critical to move it into the world of risk assessment, okay? We must move away from these qualitative preconceptions, which is size of the buffer is really what controls the mitigation. Because then we get surprised, and it's not just that, it's many other factors like we saw there. So we need to really make an effort to include objectively everything that could be, or that we could potentially, possibly consider, and then do an assessment of all those components to ultimately determine the relative importance of them. We have a tool, I haven't talked about that. We talk about that in our modeling courses. It's called global sensitivity analysis, which allows us to do precisely that. Globally assess all these factors and determine the relative importance of each one of these components. Okay? And ultimately, there are tools now already in production that can be used in the regulatory context. And now the next challenge is, how do you harmonize? How do the different agencies use these products? How can we get into a common environment where we achieve this transparency in the regulatory process and also ensure efficiency to reduce environmental impacts of the pesticide or the agriculture or land use in general, okay, to ensure sustainability of land. This is just a summary of, it's the right thing to do. I will leave it there. I want to leave you with two important quotes, okay? The first one is that all models are wrong. Some are useful, including mine. Okay, we need to be reminded, particularly us, the modelers, that our tools are not infallible. In fact, they are very limited and wrong. By the way, this quote is given to this box, but apparently he stole it. This is a famous academic from, I think he was in Princeton, and he had a good friend in the patent office in the US, Nin, and apparently they were talking about it, and he caught the quote and made it his, and so there was an appropriation there, something to be discussed. And then remember also the last of these quotes, which is GIGO, garbage in, garbage out. So remember, that it's not just about the model, it's about how we parameterize these models. I leave you with the gators, because we are the University of Florida, and that's our symbols. There is a reference there if you want to look further into this. And thank you very much for your attention and questions. I don't know if we have any time left, because I think I went almost on, to the edge. But if there are any questions, I would be more than happy to talk to you guys. Thank you.
Thank you very much, Rafa. So yes, we have time for questions.
I have a question.
Please.
So are there any models or equations that exist for buffers that don't just include grass? Like, say, including trees or shrubs, or is that just way too complicated?
Interesting. That's a very good question, because indeed there are differences, okay? And there are additional functions that, so we divide these vegetative filter strips. The term I use are mostly the previous part of that vegetation sequence, which is mostly maintained vegetation, grassy vegetation, dense vegetation. But then there is the lower part of that, which is the edge with the water, which is spontaneous vegetation, what we call riparian areas, okay? So riparian areas are more spontaneous and they have more woody species, embedded between. And so the main function of the first part, the grass buffers, is precisely runoff, surface runoff treatment, okay? And then the lower part actually, because of the deep roots, it actually can trap, dissolve subsurface flow moving into laterally into the stream. So the roots can actually pump up some of those chemicals as well. And there is a lot of work that has going on in that one. However, in terms of the surface physical processes, VFSMOD, actually in my dissertation, I developed it and tested it with grass on the top and a riparian area on the bottom. So the first paper we published on this thing had a field testing with both the riparian, which was sparse, more woody, different kinds of vegetation characteristics, and also with the grass above. And so we gave efficiencies of the model in both. Physically speaking, and this is the advantage of a mechanistic physics-driven approach. Vegetation, it doesn't matter, if it's separate, coarser, different surfaces and so on, is the same, meaning that I can parameterize it properly. So in other words, the things that the model considers when defining the vegetation are a spacing of the stems, a specific rugosity of the surface of the stems, and the size, the shape of the stems, flat, rounded, and so on. So between the roughness of the surface of the stems and the shape and the sparse, you can define any type of vegetation with respect to surface flow. And then you can modify the added effect on infiltration by modifying the potential difference in soil structure that the different types of vegetation could incorporate into the ground. So physically, you can incorporate different types of vegetation. And I can already tell you that, of course, the trapping of particles is less efficient with coarse, with sparse vegetation. So you really want to have close vegetation for the maximum removal of sediments. But in terms of a liquid phase, infiltration is really the size of the infiltrating plane that defines how much of that dissolved chemical is moving into the ground. Okay, but the important thing is that with the mechanistic model, you can actually accommodate the model to describe different set of conditions. So when people ask me, can it work in riparians? I answer, if it was empirical, maybe not, because the equations will be just specific to the type of vegetation. By being physical, I can parameterize it by incorporating the characteristics in different settings. Okay, thanks. Other questions? Yes, Rachel.
You mentioned the cold testing. I'm just curious, how do they, maybe you mentioned this and I missed it, but how do they establish the baseline for the output results to assess accuracy? Yeah,
cold testing is very is widely used in many fields. Okay, there is in fact organization. It's called MIP, a Model Intercomparison Protocol, and this started is now used, for example, in climate models, in climate change models. It's a protocol, okay, which has certain rules. And interesting enough, the first where this protocol was put together was in the with hydrological models. So, and then everybody took it after that. But the rules are set, which is you're given the inputs for each one of these testing cases. And I withhold the outputs. I tell you what I want to get. So in other words, how much flow, sediment, and pesticides reaching the other end of the buffers. And I don't give you those to you. But I give you everything else. I give you the soil characteristics, the rainfall, the chemical characteristics, the amounts coming in into the buffer. So everything that you might need with any type of model. And even we have looked previously at, I mean, the people that organize these intercomparison exercises, they look at the common set of parameters, factors that might be needed for every one of the models. And they give more information that might be needed for any given model, so that anybody that wants to apply, the model could apply to their conditions. Okay, so they study all the models that are going to be used without telling the people that are going to use them. They give all the information that might be needed to parameterize their models, and then they give them all the inputs. Okay, and then they go into their own corners. They do their the parameterization checks, whatever they need to do, and then they, in an envelope, they put back the results. And then the day comes when everything is open, and then they are compared and they're ranked, like I showed you in terms of errors. Okay, so does that answer your question?
Kind
of. So the standard was the observed values in each one of those studies. That's what you're asking. Okay. So every one of those studies had an experiment behind, where observed data was available, and the objective was to match the observed data. Yes, sorry, I did not make it clear. Yeah, I see what you mean. Okay. Somebody else. I have black boxes, which is another form of modeling, by the way, and not very good, which are most of you, and then I have a few cameras. So, okay. Well, if you're intrigued by any of these, just shoot me an email. Yes,
I have one question, Rafa. So these vegetative buffers, right? They are aimed to decrease the carbon transport through runoff, right? But it seems that they're also able to capture the pollution, right? And what happens when the pollution is captured and when you have these subsurface transport, like preferential flow? So you may look, I mean, this may demonstrate that you have decrease of pollution of the river, at least for some time. But what happened to the contaminants when it's being sent out to the groundwater and possibly the groundwater discharge of the river? So,
yeah, this is a very important question. This is the one that we need to be concerned about. No, and part of that is the fraction on the surface that I presented for the remobilization and degradation model takes care of the surface component, but not the subsurface, which is what you are referring to. The two algorithms that we use for infiltration can give us time of arrival. You know how deep into the ground the chemical moves at the end of the event, but we don't track it beyond that. So all we can do at this point is tell what is the risk with respect to a shallower table, how far it moved, or simply into the profile, how far it moved. Now, in that respect, the regulatory environments, interesting enough, they separate it totally. There is a bifurcation into the regulatory process, which is surface water assessments and subsurface water assessments. So for the subsurface, they have their own models that track the movement of the pesticide deep into the ground to see how far it might get. And that's Pearl, and in Europe, Prism also has that capacity in the US. So there are models that do the subsurface tracking. which is separated from the surface tracking. However, you have to consider many things that we know. Christophe, preferential flow is a very important one. But maybe one message here is that the highest risk is when there is very little time between the event and the receiving water body. There is no mitigation time in between. Mm-hmm. So the thing to remember about runoff is that it's very explosive. It just happens and immediately you get the chemical into the water. There is no time for degradation allowed.
Yes.
Okay. Where in the subsurface, hopefully the vadose will do a little bit of degradation, depending on the conditions down there. You might get some degradation attached to the vadose. I think we do, because that is the reason why we have a massively kill every single aquifer that we have at our disposal, because the vadose, luckily, is working for us. Okay. Otherwise, we could have already got rid of them. And so hopefully there is some degradation attached to that, but it has to be formally assessed on the other part of the system.
Okay. All right.
Very important question, though. And by the way, often you're going to find people that don't want to hear about these things. Never mind. Continue plowing on and do your work, because sooner or later, guess what? They will come back to you. And then you will have another project. So for example, the project I was telling you about, pesticide remobilization, is paid by Bayer because early on they didn't want to know about it. Now they're in the middle of a dispute and they need to have information. So if you go ahead, you will be at the position where you can capture interest down the road. So we have to anticipate those questions. Okay. All right.
If you don't have any more questions, I would like to thank you again. Thank you very much for your
Thank you guys for staying. And all right.
Thank you.
Thanks.
Thank you, Rafael. Take care.
Thank you. Thank you.